Hello and welcome to this tutorial on simple linear regression from Analytics School Online. We are finally here at part 3 of this series, the analysis section. Let me tell you, it is one of the most crucial parts of a linear regression model. It is a little advanced though, as we have just started building our fundamental knowledge on data analytics. But this is important in the sense that it is a feedback of our hard work, the hard work that we've put in to create our regression model. This is where we get to know our personal standards in analysis. This is where we analyze our analysis. That's right. This is what we are going to do. We are going to create this analysis section every time we create a linear regression model. And thus, what have we done so far? We've read the theoretical concepts about simple linear regressions. We've seen what are the things that we need to keep in mind, what are the things we have to do, and what are the things we have to eliminate. Then we started practicing and implementing our simple linear regression model with Microsoft Excel, and we finally got the summary output. And finally, we are here in this analysis section where we evaluate the accuracy of our model. Now, what is our aim for this tutorial? The basic or the most important primary aim for this tutorial is to read and understand the summary table, to understand as a whole what the summary table signifies, what it does actually tell us, and what are the things that we can take out of it and improve our model, improve the accuracy of our model, and create a better predictor. So let's move forward. Now, this is what you can see, what we had observed in our Excel summary of the output. Now I have marked the 3 parts of this output. The summary output, as you can see in this blue box, is the regression statistics, which gives us the overall preview of how good our model is. Then there is the analysis of variance. Well, this is a little crucial concept and a little advanced compared to our present standards, as we've only started learning regression. And the final one is the most important and probably the most easy to understand table, which is the model statistics part of the summary output. We'll get to understand all 3 of them moving further. Now, regression statistics. Well, this is basically an overview or a rough understanding which you can get from your model. Now it has various parameters. You can see the multiple R parameter, the R squared parameter, the adjusted R squared, the standard error parameter, and the observations. Now getting to the simplest things first. Observations is basically the total number of data points that we had in our model. If you can recall well, we actually used around 250 data points to train our model, and then use the rest 50 of the data points to predict our model. So observations is basically the total number of data points, the total number of samples that we had in our data. Now let's come to the important thing. What is multiple R? Now multiple R is basically a correlation coefficient. Now what is a correlation coefficient? A correlation coefficient is the quantity which defines the strength of linear relationship. As we are studying linear regression, our relationship must be linear, as we already know, which we plot initially to move further with the model. So this correlation coefficient or the multiple R parameter basically tells us the strength of our linear relationship. And as you can see, the value of 0.9946, basically 99.5% approximately, is a very high value, and it tells us that our model is very much linear. It has a great strength, and we can definitely call it a linear relationship. The second parameter is the R squared parameter. Well, it's basically just a statistical term, and as easy as it sounds, it is perfectly relatable. It is R squared. With the value R here, the multiple R, 0.994 here, if you just square this value, you will get this value. Multiple R squared is basically a statistical term. It is used to determine the coefficient of determination. It just tells us what is the effect of X on Y. I mean, what is the change that occurs in Y once we change a unit of X, and it is mostly used in statistical tables. It is a very defined formula. You can easily search and get to it on the internet. Now next coming the adjusted R square. Now adjusted R square is presently, as we shall understand, you don't have to worry about it if you don't understand it right now. We'll get to it in the multiple linear regression concept. So it is basically a modified version of R squared. What it does is that it does not change if you simply increase the independent variables. Now as we know, that in linear regression we've only considered one independent variable, but in multiple linear regression we are going to consider multiple independent variables, two or more independent variables. So what happens and what has been observed is that the value of r squared always increases if we increase the number of independent variables, which is not supposed to happen, because there can be existing correlation between our independent variables. Our independent variables might not be right for the model, and if the r square value simply increases with addition of independent variable, it gives us a wrong hint. So we use this criterion, the adjusted r square criterion, to understand how addition of variables in our model affects the model. Coming up to the standard error part. Standard error part, as you can see here, is basically the standard deviation of errors. It tells us the precision of the coefficient of our regression model. Standard error basically defines how much does our error value differ from the mean value of the errors. Remember when we actually looked at the legendary simple linear regression model, the term epsilon right over there, the epsilon term was actually the error, and once we start calculating all the errors, this standard error is calculated by calculating the standard deviation of those errors, how much these errors vary with respect to the mean value of those errors. Now we have done with regression statistics. Let's move on to the ANOVA table. ANOVA table is basically the analysis of variance table, and as the name suggests, it analyzes the variance between different quantities. Now what are these quantities? Let's get to them one by one. Now as you can see, the DF written over here is basically, it stands for degrees of freedom. Now how do you calculate degrees of freedom? I'll give you a simple formula. The degree of freedom for the regression model is basically the total number of variables minus 1. So because we had two variables y and x in our regression model, simple linear regression model, so the total number of variables was 2. When you subtract 1 by 2, you simply get the value 1. So our degree of freedom is always 1 less than the total number of variables that we have in our model. Similarly, the total number of degrees of freedom is basically our total number of observations minus 1. Let me tell you this about the degrees of freedom. The degrees of freedom are always 1 less than the total number of observations we have. For total number of degrees of freedom, it's basically the total number of observations minus 1. As we had already seen that our observations was 248, as you can see over here. So you basically subtract 248 minus 1 and you get the value 247. Now what is the residual degree of freedom? Actually, the total degree of freedom is equal to the sum of the regression and the residual degrees of freedom. So to find residual degrees of freedom, you can simply subtract variable degrees of freedom from observation degrees of freedom and you can get the value 246. Moving on, SS or sum of squares. Now as the formula given here, there are two types of sum of squares, the regression sum of squares and the residual sum of squares. Now the regression sum of squares is the sum of squares of the difference between the predicted values of y and the mean values of y, and the sum of squares of residuals is the sum of the squares of the observed value minus the predicted value. So these two basically give you the idea of how our data is distributed, how better is our prediction. So the larger the sum of squares, the more you can say that our data is not well adjusted, and the lesser the sum of squares, you can understand that there have been very tiny differences or minute differences between the mean values and the predicted values and observed values and the predicted values. Next comes the mean sum of squares. Well, it's not so important presently. It is basically the sum of squares divided by the total number of degrees of freedom in each class of regression and residuals. And finally we have the significance F. Now F is a statistical tool which helps us analyze the accuracy of our model, and in most cases it is a probabilistic term which tells us how varied our data is in our data set. For you to understand it, basically it gives us the probability that the regression model and the relationship defined by the regression model is by chance. Now what do you mean by chance? Now there can be cases when two variables are actually not linearly dependent, or there can be cases where two variables might not be linearly related, but because of some errors or because of defaults in our algorithms, we might get a linear relationship. So the significance f value tells us what is the probability that this relationship that we have acquired from the model is by chance or is by luck. So the smaller the value of significance f, the better is our model. Moving on further, this is the final part of our summary table. It is the model statistics, and this is what we have in our primary interest. Simply, as I explained in the Excel tutorial, we can get the predictor equation or the equation of our simple linear regression model by simply observing this coefficients and this coefficient of x variable in our model statistics data table, and we can just simply put these in the values of b0 and b1 and get to our predictor model equation. Moving on further, t-stat or t-statistic is basically another statistical tool which can help you to understand the accuracy of your model. It is basically the coefficients divided by the standard error. It gives us a measure of precision of our coefficients. And then comes the p-value statistic. The p-value statistic actually helps us to compare how our model changes when we add or subtract a particular independent variable. It will be put to much greater use in multiple linear regression. It is the value that determines the accuracy depending upon a particular significance level. A significance level, it is the level which you set in the beginning of analyzing your data, which you want to keep as a barrier, as a stable point to define your data set, where you do not go against this barrier and create your model. So it is basically a level which gives you a particular significance, and you can arrange your data with respect to that particular significance level. What you're seeing over here are basically confidence intervals. These are the confidence intervals of these intercepts and independent variable coefficients. These basically give you the range between which you can vary the intercept and independent variable x values and still get better results. And that was it for model statistics. Moving further, we finally have the final equation, and we put these values from the intercept column and the x cost price column from the model statistics. And finally we move ahead and let's talk about errors. Now most of you would think that why are we talking about errors? They must be minimal, that is all we care about, but it's not so. There have been observations in data analytics where errors were minimal, but errors used to have a particular relation between themselves, and later it was found that there was some correlation between the independent variables, or in some cases with the dependent variable, that caused this, and actually the model which we created and the precision which we got was in fact not so. So observing the residual errors is what we must do. Now it is very easy to create a residual plot. In the regression analysis bar, or the toolkit that we use for regression, it has a checkbox which names a residual errors plot, and once you plot it, you are going to get this graph where you can see that the errors are distributed amongst the x-axis, our independent variable axis. And just to give you the idea that the errors must always be distributed in a random manner, they must not have any form of relationship between them, linear, non-linear or any kind. The relation should be absolutely normal, which we often define as a normal distribution, where the errors must be distributed equally above the x-axis and below the x-axis, and their distribution must be absolutely random in all cases. If we actually find out that our residual plot is having some kind of known distribution, we must change our variables and execute our model again and again till we get a residual plot which is absolutely random. This is very important, so keep this in mind. And finally, this was fun, right? But we still have a long way to go. Regression is very, very basic and fundamental. We have much more complex and advanced topics to cover up, and they are coming up in this series. But don't worry, I'll guide you through it. I hope you learn and enjoy analytics. That was all for this series. Keep well and keep analyzing. See you soon. Thank you.